right. Good morning, everyone. Welcome to the final day of DevOps Belgium 2025. It's been a great conference so far, so let's get it started with a bang on a Friday morning. Welcome to Architecture as Code. This is a book project that I'm working on right now with my co-author, Mark Richards. And if you're familiar with our previous books, Fundamentals of Software Architecture and Software Architecture, the Hard Parts, we've been trying to quantify trade-off analysis in software architecture, making trade-offs one of the key things in software architecture. And we've spent some time thinking about how architecture intersects with other parts of the organization. Software architecture is unique amongst engineering activities in that we have a unique perspective on projects because we can see lots of things that other people can't see. We understand technical capabilities, we understand business drivers, we understand constraints, we understand the tools and platforms that we're using to build software, and so that gives us a unique perspective on the world. And virtually everything that happens in the software development ecosystem has the possibility of impacting something in software architecture. This is what we're referring to as the intersections of architecture. So we started trying to delineate how many parts of the software development ecosystem intersect with software architecture, and more importantly, how can we describe that intersection of all these pieces in software architecture. And it turns out that what we're talking about here is a nexus, but it's more than a nexus, it's a combination, it's more than one nexus. And there's a great word called nexus with a little hat over it, which means that it's the plural of nexus, which means it's more than one nexus. And that's exactly what this is because they overlap and intertwine with software architecture. I wanted briefly to call our book Architectural Nexus, but then we realized no one on earth would buy it because no one would understand what it means with the weird little hat. And so we're calling it Architecture as Code instead because that's the way we're describing these intersections with architecture and the other parts of the ecosystem is through code. We talk about the intersection of architecture and implementation, which is pretty obvious. We have to implement an architecture to actually make it function. But we also talk about the intersection with infrastructure and with data topologies. There's a giant intersection there with engineering practices. Lots of the decisions that architects make are around engineering practices, and they have consequences for your software architecture. We'll see examples of each of these. Even team topologies. We're late to the game on this. Many years ago, we started realizing what kind of impact team structure can have on productivity, and then the Team Topologies book really highlighted that. Systems integration, when systems have to integrate with each other. We also see intersections with the business environment and the way we make decisions about the business. And of course, the enterprise. There's actually a special role called an enterprise architect that deals with that intersection, but we got some new insights in that. And of course, it's not possible to do a technical talk in 2025 without mentioning generative AI. But it turns out this is really coming at a perfect time for us, the wave of agentic AIs, agentic capabilities, and MCP in particular, as you'll see, has come at a perfect time for us because it solves one of the long-running problems we've had in applying this approach in the past. It is nicely paving over that difficulty. What we're doing here is defining how architecture works through code and ultimately through this mechanism of architectural fitness functions. This is really a governance process for structural design, operational behaviors, and process, software development process. But all of these can be described in code using architectural fitness functions. So architectural fitness functions is something that I introduced in my previous book, Building Evolutionary Architectures. It is what we call the mechanics of evolving your architecture. A fitness function is sort of like a unit test, but for an architectural concern. But it's different from a unit test in that it's much broader because some architectural concerns are operational, like scalability. I can't really run a unit test to measure scalability, but I can create a monitor for that. So fitness functions encompass things like monitors and chaos engineering and anything that allows you to validate some part of your architecture that you really care about. That's the language we're going to use to describe these intersections because it's executable. What this allows us to do is not only describe the intersection, but also govern it to make sure that that intersection is not having a negative impact on our software architecture. That's this idea of architecture as code, being able to describe those things in objective, executable ways so that you can validate and get feedback on what's broken. And that's the first really important thing I'm going to say about this IP this morning, is that we're using testing tools to write some of these fitness functions. But this is not a testing framework. It's a feedback framework. What we're enabling is for architects to get the fastest possible feedback when important things change in their architecture. And it's really important to understand that, because when a unit test breaks, that's a bad thing and you need to immediately fix it. But when one of our architecture's code intersections break, it's a placeholder for conversation. If I've defined a structure that I want in my architecture and somebody deviates from that structure, that's not an excuse to take them out back and do some sort of punishment. It's a conversation. Hey, I noticed you added a new component. Do we need a new component there? Is there a reason for that? Or did you add it by accident? The point of this is we find out the day that it's added, not 3 months after it's added and gone to production. It's like, what is that component doing there? We never designed that, and having that conversation early is the essence of agile engineering, is building the fastest possible feedback for critical things. And this is what we do for software architecture. Now, one of the problems that we have run into, and in fact, you may have wondered at some point, I see books about software architecture, but none of them really have much source code in them. There's a really good reason for that. Because as soon as you put source code in a book about software architecture, you immediately carve your audience down to about 20% of what it would normally be. Because if it's C# code, then only C# developers are really going to care about that book about software architecture. And in fact, the other hazard of putting source code in technical books, one of the things that I say a lot is that every line of source code in a technical book halves the shelf life of that book. Because software is constantly changing and moving and evolving. Even the mighty Martin Fowler eventually had to write a second edition of the refactoring book because he became embarrassed that all the examples used Java util vector, which got deprecated a decade ago, and it was still there in his book, and he had to do a second edition. So one of the ways we've been thinking about attacking that problem is writing all of our examples in pseudocode instead. And that actually has two distinct advantages. One, pseudocode is purely intentional, so you don't get tangled up in syntax about how to create strings or enumerations or any of the sort of syntactic chrome that a programming language adds to you. The other nice thing is it's cross-platform, and so you can think about that even if you're an architect who supervises a Java project, a .NET project, etc. And so we created a very lightweight language for the use of our book called an architecture definition language. And it's really just a very simple declarative language with a few sort of pseudo keywords in it. Ours is very, very loose on purpose. We don't want to create a grammar or any kind of compiler or anything crazy like that. There are actually efforts going on. If you're interested in this, there's an open source effort called CALM, C-A-L-M. It is by financial networks, FinOps, and they are building an open source architecture definition language. It's more elaborate than ours. They're actually building, theirs is going to be Turing complete, which is, ours is not. Ours is really just a way of expressing intent for fitness functions. But here's the thing that we realized a little while ago, and then we're actually shocked at how well this works. When you write your architecture description language in pseudocode, you can then take that pseudocode and hand it to generative AI and ask it, would you please build me concrete fitness functions that implement this pseudocode? And it does amazingly well at this. We're leveraging the second L of the LLM, which is about language translation. And we actually thought, okay, we're going to have to tweak our pseudocode a lot to get it to produce useful fitness functions, and we did not have to tweak it much at all. It's really amazing, and I'll show you some examples of how good it is at doing that. What this allows you to do as an architect is have a simple declarative language that states your intent and then generate concrete fitness functions for Java or .NET or Python or TypeScript, JavaScript. There are frameworks and libraries in all those platforms, and that allows you to stay language agnostic. You can also use this to generate monitors and other things in your ecosystem and write custom fitness functions and leverage things like observability. So let's actually talk about this and show some examples. What I'm going to do is do a quick overview of each of these intersections. We actually have an entire section of our book for each of these intersections. I'm just going to give you a flavor of each one of them in the time I have left here this morning. First one we're going to talk about is the intersection of architecture and implementation. This one is pretty obvious, so obvious in fact that there are frameworks and libraries that help you build these. This is exactly what ArcUnit and NetArcTest and NetArcTest allow you to do, is test the implementation details for your project. So let's say that I have this little ticketing system. Customers and tickets and surveys, etc. I have these components and I have these relationships between those components. I can write some ADL that defines what I want my domain to be. Define my system as a sysops, define a ticketing domain, a customer domain, and a survey domain, and then all of these ADL statements always end with one or more assertions. So in that way, it is like a test case, but what we're asserting here is that some intent that we wanted as an architect for this design is in fact being implemented. Now, of course, if you look at this so obviously we have entries for each of those domains. If you look at this in, for example, a Java ecosystem or most ecosystems, what you're really talking about here is the directory structure, because Java forces the package and the directory structure to correspond with each other. Package names have to correspond to directory names. That's often a convention adopted in the .NET world as well. So when we define these domains, we're really defining where people are putting code within their ecosystem. When you hand this over to something like ChatGPT, it'll first parse it and figure out what your intent is, and then it'll create a concrete fitness function for you. This is in ArcUnit for Java that says this architectural definition rule, build a rule that says everything should reside in ticketing, customer, and survey, and then check to make sure that that constraint is true. And here's a similar test in ArcUnit Net, which is the .NET library. Types that do not reside in namespaces should be empty because these subdomains are not allowed. This allows me to define basically the blueprint of what I want my architecture to be. Now, this is a good example of directory structures equal packages in the Java world. And so if some developer creates another directory in your source path, in your root path, they are creating another component. And this fitness function will fail when they do that. But again, it's not a testing framework, it's a feedback framework. This is feedback I want as an architect. Hey, somebody's added a component. Should that be there or not? Is that a mistake, or is that a legitimate design evolution that I need to consider? The point, though, is you get the feedback right away. That's the key here, is we're building a system that allows you to get the fastest possible feedback when things change in your architecture that you might want to make a decision about or observe. So this lets us define these domains and components, subdomains, and assert that all of these things exist within the structure that I've designed as an architect. And of course, what that does is validate that all these things end up in appropriate directory structures, as we saw before. Hand this off to ChatGPT, and it will generate code that validates to make sure that all of these things live in the appropriate place. So this is a really easy mapping because we already have tools like ArcUnit. They already know about structural packages, et cetera, in Java. And so this is a pretty straightforward mapping. Now, it's worth saying here that ADL is purely a convenience mechanism. If you are in a Java world or a .NET world, and you're always going to be a .NET world, and you don't care about having that intermediate version, just write this and keep this forever and maintain this, etc. But we'll see that the ADL idea has some interesting benefits outside of just being able to translate that into concrete fitness functions. But let's talk about the intersection of architecture and infrastructure. We have a product owner that says the order submit API must scale to 5,000 concurrent customers with an average response time of 600 milliseconds under load. That's our aspirational goal. And the architect says, okay, no problem. Where is this information documented? Hopefully somewhere. Hopefully even something like an architecture decision record, or ADR, which is the common way that we mostly capture these kind of decisions in software architecture, which is a good idea. We have to document this stuff somewhere. And the nice thing about an ADR is it gives you the pathway to the decision. The purpose of an ADR is not just to document the results of the decision, but the context. Why are we making this decision now? What's the background? What are the side effects? All the things so you don't have to do all that research again. That's what you're supposed to capture in an ADR. The problem with that, though, is that there's a lot of detail in there, and if ultimately I only care what the end decision was and not the rationale, I have to wade through a lot of stuff. This is particularly true if I'm not a developer or architect, but still need to consume some of this information. And of course, additionally, how do we verify that this is true? The order submit API must scale to 500,000. We said that before. Okay, no problem. Here is the way we can describe that in ADL. It's an operational capability, scalability for the order submit API. Max user load is 5,000. Average response time is 600 milliseconds. And now we can assert that the average response time at max user load is under that threshold. This is the outcome of the ADR. Now you create a section in your ADR that says ADL, which is just this. This is the tersest possible outcome of that decision. And what's nice about this is you can hand this off to infrastructure team now, and they don't have to read your whole ADR, and because they don't care why you reached that conclusion, and they just need to know what we need to implement now, and this is the simplest possible way of expressing that, is in this very succinct language. And now we can write something like a custom fitness function wired into a monitor to actually determine that, and use observability tools and other platforms that already exist, Datadog, et cetera. Tools like that all give you these capabilities. And what we're looking for here is over time, as our number of current users goes up gradually, we want the average duration to stay more or less the same. Now, it's okay to get fluctuations when you have highly scalable systems, but as this slope goes up, we want to be able to measure and verify that that slope stays the same. That would be a monitor or something that's validating that, but we've documented that and the intent in our ADL. One of the big intersections is around data and data topologies. This really came to the forefront when microservices became a really popular architectural style, because microservices insists on data fidelity. That's the thing that really differentiates it from event-driven architectures from the past, because event-driven architectures in the past still tended to use one or just a few databases, not this database per service or bounded context idea that, of course, is the undergirding philosophy of microservices. And so as soon as we had to start worrying about data fidelity in software architecture, this became a big deal for software architects. There are lots of things we have to think about in terms of architecture and data and its intersection. Things like data consistency. You, of course, are familiar with the concept of eventual consistency in microservices, because that is the preferred way to do this, rather than try to implement some sort of pseudo-transactionality in that world. But a lot of architects and developers think that it sort of ends at eventual consistency, that you've given up all the other good things in the relational database and you can sort of get some consistency back. But it turns out you can have eventual all the things in your architecture. You just have to write it yourself. So one of my pet peeves is that particularly data engineers who view relational databases in particular as these magical things that do all this magical stuff that can't be done otherwise, like referential integrity checks. That's magical in a relational database because you just wire up the relationship and it checks it for you in real time, never fails. But referential integrity check is a governance activity, and the relational database is one implementation of that governance activity. But it's not the only implementation of that governance activity. It's not uniquely possible in just a relational database. You can do it in other places as well. I'll show you an example. We have an architect who says, I decided to split the database into 2 domain databases for better fault tolerance, change control, and scalability. This often happens in distributed architectures. One database has gotten too much traffic, too busy, not scalable enough. Let's split it into 2. Okay, great, but the product owner says, make sure we don't lose any trouble tickets and that both domains have the same tickets at all times. This is data consistency, which is easy if you have a single relational database because the database manages that for you, but we don't because we've now made the decision from an architecture standpoint to split that into 2. Where is this documented and how is this verified? We can write this as ADL, as an ADR, there's our architecture decision record, but we can also write the result of that in ADL, define these systems, and assert that tickets must be consistent across domains. That's our assertion, that our intent in our system. How do we implement that? Well, this is an example of writing your own custom fitness function. There is not a really nice comprehensive library like ArcUnit that you can download, which is true for most things in software architecture. It's sort of funny. When I joined ThoughtWorks many years ago, it was in the height of the open source boom. And every developer, as soon as a new problem came up, their first instinct was, oh, I'm going to write an open source framework to solve that problem. And you had to tell them, no, don't stop. Let's go check in Google and see if there are not 20 others that already do that, which there always was. But there was this knee-jerk reaction, we've got to write it from scratch. Now the pendulum has swung completely in the opposite direction. When you talk to an architect about something like this, their first question is, well, where is the comprehensive framework that I can download that's open source and I can set a maximum of 5 configuration parameters to do exactly what I want to do? Oh, that doesn't exist? That's a problem not worth solving. There is a middle ground between those two worlds of boiling the ocean to solve something or finding the ready-made perfect thing for you. And here's a great example of that. In fact, most of these custom fitness functions that you write are not in the platform or technology stack of your target. This is another difference between testing, behavioral testing, and fitness functions. Behavioral testing is almost always in the same platform or tech stack. If you're doing a Java project, you're using JUnit or some Java-based testing framework. But here, all I really need to do is be able to define things like monitors or other small things like that. So a lot of these custom fitness functions are actually just a few little lines of scripting code. And in fact, I'll show you in a bit, it can even get smaller than that once you get to MCP. So here is my ecosystem where I have my customer database and I have my ticket processing database. But now I need to validate consistency across those two things. I can look at the number of tickets in this database, the number of tickets sent, and the number of tickets in that database. And at some time interval, I can validate that D1 is equal to S plus D2. Very simple checksum to validate that all the tickets that originated are either in process or got processed. Now, This is a little bit fragile because what if I added one and dropped one at the same time? The counts would be off. And so if I wanted to make this absolutely exact, I could do a hash of the keys of the tickets in one and a hash of the keys in the other and compare the hashes, and then they have to be exactly the same or things don't match. This is an example of doing data consistency or referential integrity at the architecture level versus inside a relational database. And in fact, you can do all the things that a relational database does: cascading deletes, referential integrity, foreign key checks. All those things can be done with architectural fitness functions in a distributed architecture. The difference is they're eventual referential integrity checks, eventual consistency versus transactional. Engineering practices. Very often, architects have to make decisions on projects that encompass engineering practices that have implications for software architecture, things like choosing version control and version control strategies, automated testing, and things like code cleanliness. Here's a classic example. Should we use a monorepo or repo per service for our microservice architecture? Which one is correct? Here's the problem. The answer is neither of them, because they both suck. But they both suck in different ways. And this is the conundrum that architects constantly face. I have two choices here, and they both have terrible aspects to them, but I have to choose one or the other. What we can do is use architecture as code to mitigate the inevitable negative side effects of choices where I have to make a choice one way or the other. So what's the big problem when you're using a monorepo in microservices? What's the big danger that you're trying to avoid here? You all know it. What is it? I heard somebody over here. What is it? Come on, everybody knows the big problem with a monorepo, right? Cheating on dependencies. Exactly. It's just too easy. If it's all in one code base, I want these things to be decoupled and separate, but as a developer, I'm almost finished with this task. I need to write this other little chunk, and oh, but look, it's already there in that other code base. It's one import away, and I could be done and move on and go to lunch. It's just too tempting, or it's too tempting to accidentally do that. This is the big problem with monorepos. This is a known problem with monorepos. And so if I'm an architect who has to choose one of these or the other, I want to mitigate the bad side effects that I know already exist there. So let's say I have an architecture like this. This is one of our example architectures. It's called Monitor Me. It's a medical monitoring system with a whole bunch of little microservices, most of which are independent. The only one that's not is that sleep service, which relies on heart and respiration, but all the others are completely decoupled and independent from one another. Let's say that all of these are represented as microservices, and we're using a monorepo to keep all of those, but I don't want you to cheat across the monorepo boundaries for the services. What I have to do as an architect, and this is one of the mantras that we repeat over and over again in our book, what data do I need and where does it live? The data that I need here is dependencies between services in my repo. I know how to check dependencies between services, so that's exactly what I'll do. I will write a ADL that basically defines what I want my dependency graph to look like for each of these services in my microservices architecture. Sleep depends on heart and respiration and no dependency on anything else, and the rest of them are completely uncoupled and have no dependencies on anything else. And I can hand this over to Java, and it will in fact generate arc unit code to validate that no one is cheating in our monorepo. This is a classic example of, you know there are negative side effects. Can you create a feedback loop that prevents that negative side effect from coming and nabbing you? We have a similar fix for repo per service as well. And we also in our book talk about feature toggles versus feature branches and how to mitigate the negative side effects of those two things, which both suck, but in different ways. We have lots of things in the architecture world that have that capability or that characteristic. team topologies is interesting because 10 years ago, nobody really thought that teams had much impact on productivity or the abilities for teams. And this book very much changed that perspective. Team topologies. This book defines 4 different kinds of teams. Now, there's an implicit assumption in this book that you're doing some sort of domain-centric architecture like microservices or something like that, because the 4 kinds of teams they identify here are stream-aligned teams, which are meant to work with as little friction as possible to deliver new features as quickly as possible in the marketplace. Enabling teams are doing things like research and development and building stuff that the stream-aligned team needs just in time so they can use that and to move forward. Complicated subsystem teams are teams that deal with things that require specialized expertise, and so analytics or machine learning or generative AI or something like that would be a complicated subsystem team. They are there to support the stream-aligned team for the complicated bits that they don't need to understand. And then finally, platform teams build platforms. They build the infrastructure that all these other teams use. When you look at architecture as code here, what you want to make sure is that stream-aligned teams are in fact moving as quickly as possible and are not being impacted by these other teams like complicated subsystem teams or not having too much impact from enabling teams. And so this is one of those places where, well, what data do I need and where does it live? Well, what I'm really looking for here is, are other teams slowing down my stream-aligned team? Well, the most way they would probably do that is by issuing pull requests for the stream-aligned team. Hey, you need to pull this code into your code base. Well, every time they do that, they have to slow down. And so I can start measuring things like how many pull requests are happening from the complicated subsystem team to the stream-aligned team. And is that cadence a good one, or is it happening too much or too little? Same for the enabling teams. And we can also look to see, are the 2 stream-aligned teams in fact independent of one another, or are there dependencies that we need to check? All those things can be validated with code. And in fact, this is an example where we may actually write an architectural fitness function that looks at things like JIRA tickets, because we're trying to figure out, is that having an impact on teams? And so you go to where the data is, and a lot of the team-based data is in the ticket system or some similar mechanism like that. Integration obviously has a lot of possibilities for intersections with software architecture. A lot of event-driven architecture patterns have fitness functions assigned with them. We introduced this idea of an architecture quantum in our architecture, well, actually starting in building evolution architectures and then through the rest of those books as well. And that's really useful for doing dependency analysis at the architecture level. So if you look at an architecture like this is one flavor of our trouble ticket system architecture that we were talking about before. This is ADL that defines what this architecture looks like. Each of these services, and then assert that all dependencies of the system exist between these listed services. This makes sure that you don't have any coupling points outside of the services that I have. So you can see that all of those are, in fact, a map to services that are already here. But you can also use this to do post hoc analysis of things like log files. So if you have log files, for example, that are in the format that you see up top there, where the first entry is the service and then the rest is a list of the dependencies for that service, you can actually use a tool or even generative AI to draw a directed graph of those dependencies. And the one that I'm really interested in, often from an architecture standpoint, is what is the longest dependency chain in that architecture. And it turns out it's UI to creation to assignment to mobile app to completion. That's the longest chain of dependencies in this architecture, and you can use a graph analysis to determine that. This is often really useful when you're looking at synchronous calls, because synchronous calls can tend to block things in distributed architectures, and you want to know the extent of synchronous calls, and you can determine that by looking at log files and making some observations from those. Intersection with architecture in the business environment. So one of the things that Mark and I built in our Fundamentals of Software Architecture book, we were looking for a way to compare architecture styles. Because as an architect, you need a way to make decisions without having to build stuff. So let's say that you've been tasked by your boss to create a new accounting workflow application. You go to your boss and say, boss, I have good news and I have bad news. The bad news is, or the good news is, I'm going to build you the objectively perfect new accounting system, absolutely flawless, as good as it can possibly be. The bad news is, it's going to take me 8 times longer than you have allocated and 8 times the budget, because I'm going to build it in each one of these architecture styles and then measure directly the desirable characteristics and then throw the 7 away that are not the best and keep the best one. That'd be awesome if we lived in that world, because we'd build a lot of absolutely best piece of software ever for this problem. Nobody lives in that world. We have to make decisions about things before we can actually build them and measure them, which is always preferable. That's where qualitative analysis comes in. So actually running tests is quantifying analysis. This is qualitative analysis, the qualities of things versus the quantities of things. When you look at these generic architecture styles, layered, modular, monolith, etc., they all are generic because you can implement basically any behavior in any one of them. That's what makes them generic architecture styles. So that begs the question, how do they really differ? Well, they differ for how well they support these architecture characteristics or capabilities. Like maintainability. Layered architectures, when they get big, are very, very hard to maintain, whereas domain-centric architectures are easier to maintain. Things like a microkernel, because it's better partitioned for maintenance. We haven't built all of these, but just by understanding the nature of what drives scalability or elasticity, you can assign these qualitative star ratings to them. And this helps you make decisions and align with the goals of the business, because these architecture characteristics inform you for what kinds of things you want, but the business is going to give you drivers for what they want as their goal for a piece of architecture, for a system. And those goals may be things like cost cutting or aggressive expansion or regulatory compliance or competitive advantage or business size or complexity, etc. So let's look at one example of these, like aggressive expansion. As an organization, we're trying to do really aggressive expansion. Well, now we can look at the characteristics that support that kind of aggressive expansion best, because we're going to need scalability, we'll need evolvability, we'll need interoperability to be able to expand rapidly. And now we can identify the architecture styles that would be most suitable for that kind of system and the ones that are least suitable for that kind of system, just by doing this kind of qualitative analysis on them. And now we can actually capture these decisions in things like ADL, required capabilities. Here's the definition of the system. We want scalability, extensibility, and interoperability, and they must exhibit those characteristics. So this is sort of a composite ADL that you will now build a scalability fitness function, a extensibility fitness function, etc. And so this sort of composes that intent in a way that you can now take and build actual things from it using either ADL or concrete fitness functions. This allows you to better align architecture with the business by looking at what their goals are and then aligning your architecture decisions with those. As I mentioned before, the enterprise is sort of a unique case. There are actually 2 unique cases for us, the enterprise and security, because both of those intersections are very, very well handled because they're super, super important. One of my colleagues at one point created a mind map of some of the responsibilities of enterprise architects in some organizations. Generally, an enterprise architect doesn't do all of these things, but they do a big subset of them typically. And this gives you a lot of opportunity to be able to define things as fitness functions within an ecosystem like this around business or technology or design patterns or complexity. A lot of code complexity or other code metrics play in this world quite distinctly. And that may be something that you want to define from an enterprise architecture standpoint. There are a bunch of things you can talk about here from the enterprise level. Security, of course, and things like zero-day security checks. Things like cross-project activities like WIP limits on experimentation with platforms or tech stacks. Global coding standards. This is becoming more and more important because, oops, I went too far back there. Global coding standards is one of the few things that we have found that you can actually impose organization-wide as an enterprise architect. So when we wrote the Evolutionary Architecture book, we were really hoping that the platforms that you could build these fitness functions for were flexible enough so that you could actually have a group of enterprise architects that spent their day writing fitness functions and then using those fitness functions to actually push their long-term goals on projects to kind of gradually increase scalability, et cetera. And that's hard to do for reasons I'll get into here in just a second. In fact, one of our largest global clients has a role within their enterprise architecture group called an evolutionary architect who is going around and writing these kind of fitness functions to do that kind of stuff. So this is an obvious place where you want to apply some sort of guidance, but there's a problem with brittleness by creating custom fitness functions, which we'll address here in just a second. But this does let you define at a high level what you want things to be able to do here. So for example, one of the things I may want to do at the enterprise level is say everything has to use a particular security library to encrypt everything that goes along the wire. And I can impose that as governance and then generate that as ADL and of course create a fitness function that says no data access cannot go through this library. Tools like ArcUnit can let you build that kind of behavior. And of course this could be custom fitness functions. You could use ArcUnit and other tools to generate fitness functions, and this leverages things like software bill of materials, which has of course become a big topic in the software world recently. So the last of these I'll talk about is this intersection with architecture and generative AI. And as architects, we mostly treat LLMs as a big giant black box, which is exactly the way we should treat it. In team topologies terms, this would be a complicated subsystem team because it takes some expertise to be able to fine-tune one of these things and to build things like guardrails and evals around it. So from an architecture standpoint, mostly what we're concerned with is the surrounding ecosystem for things like LLMs or coding assistants, structured outputs, observability. We've seen an uptick in the quality of the observability tools that allow you to see some insight into what the LLM is doing. That's part of the eval stuff that we'll talk about here briefly. These are the two categories that are most likely for us, evals and guardrails. Guardrails are really more about the behavior of the LLM and customizing input and output behavior and things like if you're building a chat bot, it can keep the context of the conversation in a guardrail. You can filter out things that go into the LLM or filter things that came out of the LLM to get rid of them. So that's really more about the behavior of the LLM. Evals are much closer to what we would consider a fitness function for the capabilities of the LLM. What kind of performance is it getting? What kind of accuracy? For things like SQL to text conversion, there's an eval that says how good is the SQL that it actually created. And this, of course, lets us do things like define rules in our architecture that says, well, we have manual grading and we have AI grading. We need to establish a threshold here that makes sure that the AI grader at least hits a threshold for manual graders to make sure that it is acceptable. This is an example of some of the emerging patterns in the LLM world of using a more expensive LLM to judge the output of a cheaper one. So you selectively send output to that one. You can do the same thing with a manual to make sure that you're getting reasonably good results from it. But I want to wrap up by talking about this intersection between architecture and agentic AI. So we've had this idea of fitness function since 2017. It actually predates that. It was Rebecca Parsons' idea, Dr. Rebecca Parsons. She was the co-author of the Building Evolutionary Architectures book, and we actually wrote fitness functions well preceding our book, and when we wrote the book, we've been doing that for a while. And we had aspirational goals that you could build fitness functions at an enterprise architecture level and each level of the architecture and be able to define executable governance. In fact, the subtitle, the second edition of our book is Automated Architectural Governance. But the problem we encountered in the real world for that is that the further away you get from a project or an ecosystem, the more brittle those kind of very specific fitness functions become. And it's the exact same problem you see in domain-driven design, where if you change the internal implementation of something and something relies on that implementation, you've broken it. And that's the whole concept of a bounded context. Keep the implementation details secret and just do well-known interfaces to get to things, and that cuts down on the brittleness of your system. And it turns out we had exactly this problem with these kind of global fitness functions. I create a code quality fitness function at the enterprise architecture level that runs on each project, but then as each project changes the details of their tech stack, et cetera, these things start breaking, and then it becomes overhead, and it's a hassle, and nobody wants that. Enter MCP, which could not be more perfectly suited for this, because when you have unique APIs that are talking to something, each one of them has to know exactly what API to call with all the exact details. But MCP creates a sort of generic integration layer for us that publishes things like, here are the tools that you have available, here are the data sources you have available from me as an MCP server, and this allows us to wire in our fitness functions using MCP and agents. This paves over all of the very specific implementation details in a project and allows you as an architect to state intent and then let the agents figure out how to make that intent come true for projects. And so projects now, from a governance standpoint, become sort of a bounded context where the internal implementation detail is kept inside the project, but the intent can be broadcast through MCP and through agentic AIs. MCP is a standard protocol, and the things that's really beneficial to us are these MCP primitives, tools, resources, and prompts. Tools are executable functions that AI applications can invoke, like file operations or API calls or database queries, or call fitness functions. Resources are data sources for things like file contents or database records or API responses or log entries that exist in my distributed architecture. And prompts are reusable prompt libraries that help you do things. For example, I want you to check referential integrity for me. This allows you to, well, here's an example of tools. I can issue a query to an MCP server and say, give me a list of all your tools, and it will come back in JSON, which is the lingua franca of this. And here's the example of the MCP weather information. It gives you required fields, et cetera. So it tells you exactly how to invoke that tool. What this allows us to do is to state intent for our agents, and then let the agents figure out how to actually make that intent come true. So for example, I can state the intent from the enterprise architecture level, validate referential integrity on this distributed architecture. And inside the project, their MCP server knows that, oh, for these two databases, I need to do a hash of the primary keys here and a hash of the foreign keys and make sure they match. But at some point, you add a third database. The project now, for the request, will add that third database and add the hashing to that. I haven't changed the enterprise architecture intent, which is validate referential integrity. I've changed the implementation detail, but MCP allows me to hide that detail, which gives me the ability to define these rules at a higher level and let agents handle the messy details of how those things work. So this is, above all, a fast feedback framework for getting fast feedback for important structural things in our architecture. So when you look at things like domain level testing, before Agile engineering, it was spotty and arbitrary. And one of the benefits of Agile engineering is we got robust, comprehensive, every time we change something, we get a broken test that tells us feedback. Now we have really good testing comprehensiveness, and we have sort of spotty architecture characteristics checks. We don't want this level of comprehensiveness for fitness functions. This is not a testing framework, it's a feedback framework. When an architect designs a building, they don't validate every single wall in the building, they look at the load-bearing walls. That's what we're identifying as these fitness functions. What are the things that I really need feedback to make sure that it's working correctly? So the reason for this, really fast feedback for architectural changes, mitigate inevitable negative trade-offs, decisions you have to make. There's some principles here. Make sure that the value is greater than the effort it takes to implement these things, because you don't want to create a lot of frivolous fitness functions. And the mantra here is, what data do I need and where does it live? I can use that to make some decisions about my architecture, and what is the smallest, fastest feedback in architecture I can create. That's the end of my time. Thank you very much. I hope you enjoyed it. Thanks. Take care.